All right, so I have not yet uploaded these to Moodle. I will do that after we finish up here, but I have written out your next two exams. So the one over MOSFET physics and single stage amplifiers is a whopping 4 problems. 2 problems having to deal with the device physics. And then 2 problems having to deal with single stage amplifiers. Why is this not scrolling? I don't want it to be. That is the entirety of the test. Hopefully much shorter and less of a pain in the ass than the first one. That's my goal here, okay? I have not yet decided on a due date. We'll talk about that in a minute. And now I'm going to show you your third exam. One problem. The problem is we are going to be implementing this behemoth in electric together over the next several class periods. This is the biasing circuitry that we have been working on for the last several days. So just in case you think I'm batshit insane, I am, but I'm also not. Oh, and I can't draw on this with this thing. Let me open it up with this. Open. 438. Fall 2022. Exam 3. All right. So as I was saying, we are going to be implementing this monstrous looking thing to serve as our bias for our op-amp circuit, okay? Now, we have not talked about all of this yet. So everything that I'm mapping out right here is what's called a beta. That looks too much like a heart. Multiplier reference circuit. That is literally what we're talking about today. This thing over to the left-hand side is the startup circuit to make sure that the beta multiplier circuit is biased at the right point, because the beta multiplier reference circuit utilizes positive feedback, so it has an astable output. The startup circuit forces it to the stable point we want. Okay. Let's see this thing over here. This is a wide swing PMOS current mirror, which means in turn, this guy and this guy are simple single transistor devices that are acting as the referent current source for that wide swing PMOS current mirror. And from that, we are going to get 3 biasing voltage, bias 1, high, and bias 2. So effectively, if we need to bias a cascode anything PMOS, we can get that. Then we have this little guy right here, which we are only going to use to bias things like 3 weeks from now. This is how we're going to wind up biasing our floating current sources that will be part of our push-pull amplifier output stage. So we're going to go ahead and integrate that into the system so that we don't have to break it later, figuring out how to get that in. And then we have a simple cascode here. And then down here, these are all part of the same circuit. We have our wide swing NMOS current mirror. Two cascade current sources serving as our biasing reference currents for that wide swing current mirror. We have another bias thing for the other part of our push-pull output stage. And then we have a little cascode here to provide the right amount of current. So this is going to be a gnarly thing to figure out how to lay out because all of this is happening between a common power supply rail and a common ground rail. And we have 8 different voltages that we need to make sure are correct, which means we can't accidentally cross any metal layers or we short everything out and it doesn't work right. So that's our goal for the remainder of the week after today's class meeting, is to be working on this. After we finish up this project, then we're going to talk about differential amplifier to move into the single stage op amp, which is nothing more than a differential pair loaded with a current mirror. And then we are going to talk about frequency compensation and then attaching our final stage, and then we are done. So this is probably the most complicated part of our op amp design. And it requires the most attention to detail, because if we get any of these 8 voltages incorrect, our circuit won't work. Okay, so that's our goal. All right. And that'll be due, I'm going to say 1 to 2 class meetings after we finish it up in here, for the people that are following along at home or whatever, to give them time to do shit. So, all right. And so we are going to talk about the data multiplier. So this is option number 3 for replacing a ideal current source with a practical something to generate a reference current. Okay. And so this is data multiplier referenced self-biasing. So as I believe I mentioned at the end of our last class meeting, this circuit is just a variation on the classical Widlar current source, where we have some reference current feeding into a current mirror. Like so. Where this is transistor M1 and this is transistor M2. But instead of having a simple current mirror thing, we degenerate the source of transistor M2 with some biasing resistor, and then our current flowing through transistor M2 is going to be equal to IREF over some arbitrary scaling factor K that is established by the size of the transistors that we used. Not particularly important to what we're doing here. This is just the baseline for where this came from, and we actually analyzed this circuit in its BJT form back in 336. Okay, so if we replace the ideal current source in this guy with a PMOS current mirror, what we will have is this circuit. I'm giving myself the room on the left-hand side for a reason, just to be clear. So this is going to be transistor M3. This guy is M1. Here is M2, our bias resistor, our bias. Here's our PMOS. Those gates are tied together, and I need to tie the gate of M3 and M4 to the drain of M4 and M2, like so. If we didn't have this bias resistor here, this would actually be an example of a Wilson current mirror. So they have all these different funny names named after dead white guys for the most part. Anyway, so let's talk about how this thing works, okay? So here is VSG3. Here is VSG4. How are those two quantities related? They're the same thing. So what that means is that M4 is carrying a current of I reference, whatever it happens to be. And M3 has to be carrying that same exact current because we have a current mirror here. So the I reference that's being sourced by M3 serves as the reference current for transistor M1, which means M1 is also carrying a reference current, IREF, and M2 has to also be carrying IREF as well, because there's literally no other place for the current being sourced by transistor M4 to go. So that exact same reference current, IREF, flows down through our biasing resistor. Now this brings us to an interesting thing here, okay? So M1 and M2 are carrying the same current, but they have different gate source voltages, right? So what I mean by that is if we look at this guy right here, VGS1, here is VGS2, they have to be different quantities if there's any reference current flowing through, because there's a voltage drop across our biasing resistor. Okay. So mathematically, we have the following case. VGS1 has to equal VGS2 plus our reference current times our bias resistance. Assuming that both of these transistors are operating in saturation, which M1 has to be because it's diode connected and M2 needs to be, or this doesn't work correctly, we are going to have the square root of twice IREF over mu n C ox W over L1 plus VTHN. Since we have both NMOS and PMOS transistors here, I'm specifying exactly which value that we're looking for, or we're using. And this is going to be equal to something similar. Twice IREF over mu n C ox W over L for transistor M2 plus that same VTHN plus IREF times R bias. So if we call this quantity theta 1, and this guy right here will be beta 2. And beta 2 we can think of as just a scaled version, K, of beta 1. If we solve this equation for the quantity I ref, what we find is that this is twice R bias squared times beta 1 multiplied by a factor of 1 minus the square root of 1 over K, our scaling factor, squared. And this allows us to solve for the biasing resistor value needed to achieve a particular reference current where we establish what that K factor is, okay? There are a couple of constraint-ish things that we need to pay attention to. The first of which is that this is a positive feedback circuit. It's stable if the loop gain is less than 1, which requires the value of R bias to be not small. And so what I mean by that is that if we accidentally shorted this thing out, so at particular frequencies, we are going to find that this could be problematic as our internal capacitance of our MOSFETs will short this thing to ground, and we have an astable system or an unstable system, which is bad. So typically speaking, a K value of 4 is used for a couple of reasons. A, it's going to make that resistor R bias large enough to where this shouldn't happen. And B, the math is really easy if K is equal to 2, because that whole 1 minus 1 over this, 1 minus the square root of 1 over K bit just comes out to be 1/2. So it's really just this part right here multiplied by a factor of 1/4. And it's a very trivial relationship to figure out the relation, what R bias needs to be to get a particular current value. Also happens that we'll have a constant transconductance, which this is also called constant transconductance biasing. So let's do a quick comparison type thing here, okay? So actually, let's scroll back because it's been a couple of days. When we used a resistor to bias things over here, we found out to achieve a 25 microamp reference current required us to utilize a 165.675 kilo ohm resistor, which, as I mentioned, is really physically large and annoying to implement. If we use the exact same process, so width to length transistor, 10 by 2, all this kind of good stuff. 0.7 volt VTH, mu n Cox is 400 microamps per volt squared. Using those exact same parameters, what we would find is that our bias, actually I can do it down here. So for IREF equal 25 microamps with VTHN equal to 0.7 volts and mu n Cox times 10/2, which is our minimum transistor size, is equal to write this down here. mu n Cox was 400 microamps per volt squared, I believe. What we wind up getting is that our bias resistor needs to be 3.162 kilo ohms. So we reduced the size of the biasing resistor needed by a factor of about 52. So it occupies a lot less space. And a change of plus or minus 5 to 10% is not going to be nearly as catastrophic as it would have been with that large resistor. Okay, so we have decreased the size of the resistor needed, which in turn lowers the temperature dependency of this circuit. Now, what about power supply voltage dependency? Any thoughts? So this guy right here governs the behavior. You see VDD anywhere? It's independent of supply voltage variation. So this is why the beta multiplier reference is used. Okay, it gets results similar to, but not quite as good as band gap voltage reference circuits, which is highly temperature independent and power supply independent without having to use mixed technology. So no BJTs and MOSFETs, only MOSFETs to deal with here. Let's talk about a couple of other useful things this guy does. So we can use it to bias assuming the gate of M4 is tied to the gate of, let's call this M6. This can serve as the reference current for other PMOS current sources, and the gate of M2 can be tied to the gate of other NMOS devices. So here's M5. It can serve as the reference current for other NMOS devices, right? So this guy should be carrying a current of IREF. This guy should also be carrying a current of IREF. So we can use this to really copy anything we could potentially want. Another advantage here, and we haven't listed any sizes in particular, but we're not required effectively to make our PMOS transistors very, very large if they're serving to as a load here, like we did in the MOSFET biasing, right? So when we did the MOSFET biasing, we had to increase the length of our devices in order to accommodate for that extra voltage. The resistor takes up that extra voltage in this case. So we can use the minimum sized NMOS devices, and then we just need to scale our PMOS devices by a factor that effectively makes the mobility effects the same. So in this case, we go back here. If we were using 10 by 2 NMOS transistors, we could use 30 by 2 PMOS transistors to get effectively the same mobility. 3 times as large, or so 3 times the width would get us in the ballpark, and everything would work pretty great. Okay. All right, so the last thing that I want to talk about for today then is forcing this thing to work the way that we want it to. So because this system is a positive feedback system, and therefore it has 2 different stable operating points, we have to utilize what's called a startup circuit to force it into the state that we want. So our startup circuit is going to look something like this. I'm going to do this in, let's not do full. let's do gray. So I'm going to put a dashed line here. Everything to the right of the dashed line is our beta multiplier. Everything to the left of the dashed line is what we need to force this thing to work in the correct way. So we are going to tie the gate of our PMOS current mirror to a transistor out here. So this is going to be an NMOS device. The source of this NMOS device is tied to the gate of M1. Like so. So we have a transistor, let's call this MS3, or the S is for startup, where the drain is connected to the gate of transistor M3, and the source is connected to the gate of transistor M1. This guy is just acting as a digital switch, okay? So it's either off, on, no other performance other than that. Okay. Over here, we have a PMOS transistor that is going to be diode connected. This will be MS2. Typically, this guy is long length. And then down here, we have an NMOS transistor that is a standard size, and its gate is tied to the gate of M1. Okay, let's call this MS1. So the unwanted state in this guy is going to occur when the gates of M1 and M2 are at ground, which in turn means that the gates of M3 and M4 are at VDD. Effectively, the unwanted state is everything is off, okay? So under that condition, the gate of our transistor MS1 is at ground as well. So it is off. And the gate of transistor MS2 is somewhere between our power supply voltage and the power supply voltage minus the threshold voltage of our PMOS transistor. So effectively, this node is just floating somewhere close-ish to VDD. MS3 will behave like an NMOS switch. So effectively, the voltage that's at the gate of the startup transistor 3 will be large-ish, somewhere close to VDD, but the voltage that's at the source of transistor MS3 is tied to ground, which means MS3 gets turned on, is able to conduct current, and any current that is conducted through it raises the potential of the gates of 1, 2, and MS1, forcing those guys to start sinking current, which in turn turns the transistors M3 and M4 on. So this startup circuit will force this thing to settle to the stable condition where M1, M2, M3, and M4 are all carrying the reference current within a fraction of a second. And once it's on, it stays on. All right, so that's what I wanted to talk about today. What we are going to do on Wednesday is we are going to take let me go back to the exam here. Exam number 3. I have a note here that says the transistor sizes and resistor value indicated in the figure aren't correct for the onsemi C5 process. They are correct for the made up process from the textbook. Okay. So what we're going to do is we are going to effectively extract what our correct parameters are going to be. So let me see if I can find this file here real quick. I think I just have it saved in my C drive. C5 models. I'm going to be putting this on Moodle for you guys. Let me move this thing out of the way. Let's try to make this bigger. Move this out of the way. This is the data collected from an actual fabrication run for a C5 process that is used to develop the models that SPICE will use to tell us how our circuit behaves. There is so much information in this thing that I honestly don't have the foggiest damn clue what it means. We can see some important things like VTH naught. That's our threshold voltage. I know what that means all day. That's great. Okay. Tox is the thickness of our oxide. So 13.9 nanometers, that agrees pretty damn well with what onsemi's press release says of 13.5 nanometers for the oxide thickness. I believe mu naught right here of 458.439 is the electron mobility. That being said, there are other things, mu A, mu B, and other stuff that I honestly don't know what those mean. So anyway, there are lots of other parameters here. I don't see anything for like lambda really jumping out at me. And then if we scroll down to the PMOS device, we have something pretty similar. We have a threshold voltage of negative 0.92. So that's a pretty big mismatch, really 670 millivolts to 920 millivolts. That's a pretty substantial difference between the two things. Our whole mobility, if the mu naught does represent a whole mobility here, which again, I'm not 100% sure. That's why we're going to extract it from a simulation. 212 would be roughly half of the other one, which means in our design here, all of the NMOS transistors that don't have a label are assumed to be 10 by 2, which is the smallest possible NMOS transistor size. And it also happens to be the smallest possible NMOS transistor size for us. All of these PMOS transistors that are not labeled are 30 by 2, which might be too large for what we are doing, right? We'd get better performance assuming that we have this 2-to-1 ratio of mobilities or close to 2-to-1 ratio of just replacing all of these guys with 20 by 2s. And we're going to do that once we make sure that's the right thing to do by simply doing 2 10 by 2s in parallel with each other so that we can get nice even lines for everything. So anyway, we're going to kick things off with running some simple simulations to extract the parameters that we need to pay attention to, like our carrier concentration. We're also going to figure out what lambda is for each of our designs so that we know what, or we can estimate what kind of output resistances and all that kind of stuff we're going to have for our different stages, and then go from there. So for the next several class meetings, it's laptop electric time. Okay. I cannot encourage you guys enough to buy a damn mouse. If you do not already have one, your life will be miserable if you're trying to use electric without a mouse. Okay. So, all right, I am done ranting.
Just laughing, your life would be miserable without a mouse. I'm just imagining generalizing that out to just anything.
I mean, it's pretty amazing that IBM pretty much gave up their patent for free.
Yeah. That was a weird time. Well, that was weird. Xerox. They basically created the graphical user interface that, that Apple and IBM, with the Microsoft stole.
Mhm.
Both stole it from the same people. Xerox had
Very
no
much
idea.
stole, yeah.
Yeah.
They had no idea what they're sitting on.
All right.
As far as the due dates for exam 2 and 3,
So exam 2, let's call it next Wednesday, and exam 3 is, like I said, 1 to 2 class meetings after we finish stuff so that you guys have time to go back through and toy around with things if you need to.
right. And by next Wednesday, you don't mean this coming class Wednesday. You mean
Good, yeah, so I mean,
Yeah, because
so let me be very specific here. The 26th of October is what I am going to list the due date for exam 2 at. And then the due date for exam 3 is TBD, but it'll be 1 to 2 class meetings after we wrap it up in here. Or at least to the level that I intend to wrap it up to.